Solution of subjective exam of civil sub-engineers. Exam conducted by Bagmati Pradesh. Loksewa IG. February 24, 2082. Quetzal, define the term surveying and differentiate between geodetic and plane surveying. Answer: surveying is the science and art of determining the relative positions of points on, above, or beneath the Earth's surface and representing them in a usable form, such as maps, plans, or digital models. It involves the measurement of distances, angles, and elevations using various instruments and techniques. Difference between geodetic and plane surveying. Feature: geodetic surveying. Plane surveying. Earth's curvature consideration. Takes into account the curvature of the Earth. Assumes the Earth is flat, ignores curvature. Area covered. Suitable for large areas, over 250 square kilometers approximately. Suitable for small areas, less than 250 square kilometers. Accuracy. High precision and accuracy due to complex calculations. Lower precision acceptable due to simpler methods. Instrumentation. Uses advanced instruments like GPS, theodolites, EDMs. Uses basic instruments like total stations, tapes, levels. Application. Used in national mapping, large-scale infrastructure. Used in building construction, road layouts, and small plots. Surface representation. Considers Earth as a sphere or ellipsoid. Treats Earth as a flat horizontal surface. In summary, geodetic surveying is more suitable for large-scale, high-precision work over long distances, while plane surveying is used for smaller, localized projects where curvature can be neglected. 2 Quetzales, explain in brief the constituents of brick earth. What are the harmful ingredients of brick earth? Answer: constituents of brick earth. Brick earth is a type of soil used for making bricks. It must have the right proportion of various constituents to produce strong, durable, and well-shaped bricks. The main constituents of brick earth are: alumina, 20%, 30%. Main clay component. Provides plasticity, which helps in molding the brick. Excess alumina can cause cracking and warping during drying. Silica, 50%, 60%. Prevents shrinkage and warping. Gives strength and durability to the brick. Excess silica makes the brick brittle and weak. Lime, less than 5%. Helps in silica fusion during burning. Small quantities improve strength and texture. Excess lime can cause disintegration or lime bursting. Iron oxide, 5%, 6%. Imparts red color to the brick. Increases hardness and strength. Too much iron oxide causes the brick to become dark or overburnt. Magnesia, less than 1%. Adds yellow tint and reduces shrinkage. Excess magnesia leads to brick decay over time. Harmful ingredients of brick earth. Lime in lumps. Causes lime bursting when it absorbs water and expands after the brick is burnt. Excessive alumina. Leads to high plasticity, causing cracking and deformation upon drying. Excessive silica. Makes the brick brittle and reduces strength. Organic matter and vegetation. Decomposes on burning, leaving pores that weaken the brick. Salts, alkalis like sodium and potassium. Cause efflorescence, which appears as white patches and weakens the brick structure. Pebbles and gravel. Prevent smooth molding and create weak spots in bricks. 3 Quetzales, Draw the bending moment diagram for a simply supported beam of 5 meter span, subjected to a uniformly distributed load of 4 knots per meter and a concentrated load of 30 kN at the center. Answer, given. Beam span, L equals 5 m. UDL, W equals 4 kN/m, over the entire span. Point load, P equals 30 kN at center, 2.5 m from each end. 1. Calculate support reactions. Let the supports be A, left, and B, right. Total UDL load equals W times L equals 4 times 5 equals 20 knots. Total load on beam equals 20 knots, UDL, plus 30 knots, point load, equals 50 knots. Since the beam is symmetric and the point load is at the center, reaction at A equals RA equals 50/2 equals 25 knots. Reaction at B equals RB equals 25 knots. 2. Bending moment at key points. At A and B, supports. Ma equals MB equals 0, since it's simply supported. At center, X equals 2.5 m. Use section method or superposition. Moment due to UDL. For a UDL over the entire span, max moment at center is MUDL equals WL2/8 equals 4 times 52/8 equals 100/8 equals 12.5 kNm. Moment due to point load at center. MP equals PL/4 equals 305/4 equals 37.5 kNm. Total moment at center. Max equals MUDL plus MP equals 12.5 plus 37.5 equals 50 kNm. 4. Quetzales, explain pipe flow and open channel flow. Answer, pipe flow. Definition. Pipe flow refers to the flow of a fluid through a closed conduit, typically a pipe, where the fluid is completely enclosed by the pipe walls. Key characteristics. The flow is under pressure. The entire cross-section of the pipe is filled with the fluid. Governed primarily by pressure differences, not gravity. Examples, water supply pipes, oil pipelines, HVAC systems. Important concepts. Reynolds number, redetermines whether the flow is laminar or turbulent. Continuity equation, Q equals AV, flow rate equals area times velocity. Bernoulli's equation, energy conservation along a streamline. Darcy-Weisbach equation, used to calculate head loss due to friction, open channel flow. Definition. Open channel flow occurs when a fluid flows with a free surface open to the atmosphere, typically driven by gravity. Key characteristics. The fluid surface is exposed to atmospheric pressure. Flow is primarily influenced by gravity rather than pressure. Examples, rivers, canals, stormwater drains, sewer systems. Important concepts. Flow classifications, uniform/non-uniform, steady/unsteady. Manning's equation, empirical formula used to estimate flow velocity. V equals 1/nr2/3s1/2. Where n is Manning's roughness coefficient, r is hydraulic radius, and s is slope. Critical, subcritical, and supercritical flow, based on the Froude number, Fr. Fr equals V/SQRTGD. Fr1, subcritical, slow, gravity dominated. Fr equals 1, critical. Fr1, supercritical, fast, inertial dominated. Count summary comparison. Feature. Pipe flow. Open channel flow. Enclosure. Fully enclosed. Partially open, free surface. Driving force. Pressure. Gravity. Surface condition. No free surface. Free surface open to air. Governing equations. Bernoulli, Darcy-Weisbach. Manning, energy equation. Common in. Water supply, oil transport. Rivers, canals, drainage. 5 Quetzales, describe soil classification in brief. Answer, soil classification is the process of categorizing soils based on their physical and engineering properties to understand their behavior for construction, agriculture, or other applications. Major types of soil classification. 1. Textural classification, based on particle size. Clay, 0.002 millimeters. Silt, 0.002 millimeters, 0.06 millimeters. Sand, 0.06 millimeters, 4.75 millimeters. Gravel, 4.75 millimeters, 60 millimeters. Pebble, 4.75 millimeters, 80 millimeters. Cobble, 80 millimeters, 200 millimeters. Boulder, 200 millimeters. 2. Engineering classification systems. A Unified Soil Classification System, USCS. Used in geotechnical engineering. Based on grain size and plasticity. Major groups. Coarse-grained soils, gravel/sand GW, GP, GM, GC, etc. Fine-grained soils, silt/clay CL, CH, ML, MH. Organic soils, OL, O. Highly organic soils, PT, PET. B. AASHTO classification system. Used for highway construction. Soils grouped from A1 to A8, based on grain size and Atterberg limits. Includes a group index, GI, indicating suitability for subgrades. Pavement based on consistency, fine-grained soils. Measured using Atterberg limits. Liquid limit, LL. Plastic limit, PL. Shrinkage limit, SL. Helps determine the plasticity and behavior of clay and silt. Field classification, visual manual. Quick identification based on color, grain feel, moisture, stickiness. 6 Quetzales, how do you differentiate short and long columns? Explain. Answer, columns are vertical structural elements that carry loads from slabs and beams to the foundation. They are broadly classified into short columns and long columns, mainly based on slenderness ratio and buckling behavior. 1. Slenderness ratio, key criterion. The slenderness ratio is defined as slenderness ratio equals effective length, L, / least radius of gyration, R. L equals effective length of the column, depends on end conditions. R equals I/A, I equals moment of inertia, A equals area. So, classification based on slenderness ratio. Column type. Slenderness ratio. Behavior. Short column. 12. Fails by crushing, material failure. Long column. 12. Fails by buckling, instability failure. 3 short column vs long column. Feature. Short column. Long column. Slenderness ratio. Less than 12. Greater than 12. Failure mode. Fails by crushing, material failure. Fails by buckling, instability failure. Load capacity. Higher, more stable. Lower, less stable. Behavior. Compression dominant. Bending and buckling dominant. Design. Based on strength of concrete and steel. Must consider buckling and instability effects. Radius of gyration. It has more radius of gyration. It has less radius of gyration. Lateral dimension. Short columns have a large lateral dimension as compared to its height. Long columns have a small lateral dimension as compared to its height. Preferred. Stronger than long column and it is highly preferred. Are weaker than short column, so generally, it is not preferred. 7 Quetzales, describe about one-way and two-way slab of RCC section with details and sketch it. Answer: slabs are flat horizontal structural elements in RCC construction that transfer loads primarily to beams and columns. They can be classified as one-way or two-way slabs based on how loads are distributed and supported. One-way slab. Definition. A slab is termed one-way when the ratio of longer span, Lx, to shorter span, Li, is greater than or equal to 2. Lx/Li greater than or equal to 2. What characteristics? Supported only on two opposite sides. Load is transferred in one direction, shorter span. Main reinforcement is provided along the shorter span, direction of load. Distribution bars are placed perpendicular to main bars. Arc examples: narrow rooms, corridors, balconies. Two-way slab. Wide definition. A slab is termed two-way when the ratio of longer span to shorter span is 2. Lx/Li 2. Arc characteristics. Supported on all four sides. Load is transferred in both directions. Reinforcement is provided in both directions. More efficient in load distribution. Examples: square or nearly square rooms. Harrison table. Feature: one-way slab, two-way slab. Span ratio: Lx/Li greater than or equal to 2. Lx/Li 2. Load distribution: one direction, short span. Two directions, both spans. Main reinforcement: in one direction. In both directions. Support: two opposite sides. All four sides. Structural depth: generally thinner. May need to be thicker. 8 Quetzales, define specific gravity, dry mass density, water content, percentage air void and air content. What is the relationship between dry mass density and percentage air voids of soil mass? Answer: specific gravity, G. Definition: the ratio of the unit weight of soil solids to the unit weight of water. Formula: G equals weight of soil solids. Weight of an equal volume of water. Typical value for soils, 2.60 to 2.75, dimensionless. 2. Dry mass density, ρ-D or gamma-D. Definition: the mass of dry soil per unit volume, including the volume of air voids. Formula: ρ-D equals md/v, where md equals mass of dry soil, v equals total volume of soil. Unit: kg/m superscript 3 or kn/m superscript 3. Water content, W. Definition: the ratio of the weight of water to the weight of dry soil, expressed as a percentage. Formula: W equals WW/WD, times 100, where WW equals weight of water, WD equals weight of dry soil. Unit: percent. Small blue diamond 4. Percentage air voids, NA. Definition: the volume of air voids as a percentage of the total volume of the soil. Formula: Percentage air voids equals VA/V times 100, where VA equals volume of air, V equals total volume of soil. Unit, percent. Small blue diamond 5. Air content, AC. Definition: the ratio of the volume of air to the volume of voids, expressed as a percentage. Formula: AC equals VA/VV times 100, where VA equals volume of air, VV equals volume of voids. Unit, percent. Link relationship between dry density and percentage air voids. The dry density of soil is inversely related to the percentage of air voids. As air voids increase, dry density decreases. Derived relationship: Na equals 1 rho d slash g rho w times 100, where Na equals percentage air voids, rho d equals dry density of soil, g equals specific gravity, rho w equals density of water, typically 1000 kilograms per cubic meter or 9.81 knots per cubic meter. This equation shows that for a given specific gravity, as dry density increases, air voids decrease, and vice versa. Section B. Briefly explain different sources of dampness in building. Answer: dampness in buildings can arise from various sources, including rainwater penetration, water enters through walls, roofs, or joints due to poor construction, damaged plaster, or lack of proper drainage. Groundwater rise, capillary action: moisture from the ground rises through walls and floors if there is no damp-proof course, DPC, or it is damaged. Condensation: moisture from indoor activities condenses on cooler surfaces when ventilation is poor. Leakage from plumbing, faulty pipes, taps, or water storage systems can cause localized dampness. Seepage from adjacent structures: water may seep from nearby buildings, especially if they are at a higher level or poorly waterproofed. Poor drainage: inadequate site drainage can lead to water accumulation around the foundation, increasing damp risk. Construction defects: use of poor quality materials or improper construction practices can allow moisture ingress. 10 quetzales, explain the canal losses and their minimization methods. Also, draw a typical canal irrigation system showing major components. Answer: canal losses in irrigation systems. Canal losses refer to the loss of water that occurs during conveyance from the source to the fields. These losses reduce irrigation efficiency and can be categorized as follows. Types of canal losses. Seepage losses. Water seeps through the bed and banks of the canal into the surrounding soil. It is the most significant loss, especially in unlined canals. Evaporation losses. Loss of water from the surface due to sun and wind. Higher in hot and dry climates. Absorption losses. Water absorbed by dry canal soil and vegetation along the banks. Percolation losses. Water percolates deeply beyond the root zone, especially in sandy or gravelly soils. Transpiration losses. Loss of water due to plants growing along canal banks. Operational losses. Loss due to poor management, including spills, overflows, and leakage at control structures. Minimization methods for canal losses. Seepage control. Lining canals with concrete, brick, or plastic membranes. Compacting the canal bed to reduce permeability. Evaporation reduction. Reduce the exposed water surface by using narrower and deeper canals. Grow windbreaks or trees to reduce wind velocity. Vegetation management. Regular clearing of weeds and plants along canal banks. Efficient operation. Use proper scheduling and control gates to reduce spillage. Employ modern irrigation management techniques, like automation. Maintenance. Regular repair of leaks and maintenance of control structure. 11 Quetzales, what is the importance of camber in road pavement? How it is provided? Answer, importance of camber in road pavement. Camber is the transverse slope provided to the road surface, usually in the form of a slight convex curve. It plays a crucial role in road design. Importance of camber. Efficient drainage. Ensures quick removal of rainwater from the road surface to the sides, preventing water stagnation. Prevents water infiltration. Reduces the chance of water seeping into the pavement layers, thus preventing damage like potholes, rutting, and cracking. Increases pavement life. By preventing water accumulation, camber helps in prolonging the lifespan of the pavement. Improves safety. Minimizes the risk of skidding and hydroplaning by ensuring a dry road surface. How camber is provided. Types of camber shapes. Straight line, plane, camber, two straight slopes from the center to the edges. Parabolic camber, a smooth parabolic curve, more common in highways. Combination camber, parabolic in the middle and straight near edges. Typical camber slopes. Bituminous roads, 2% to 2.5%, 1 in 50 to 1 in 40. Concrete roads, 1.7% to 2%, 1 in 60 to 1 in 50. Earthen roads, 3% to 4%, 1 in 33 to 1 in 25. Construction methods. Manual leveling using templates or camber boards. Machinery like motor graders for larger or high-precision works. 12 Quetzales, explain the rate analysis of an item for cement concrete work in 1:2:4 ratios with example. Answer, rate analysis of cement concrete work, 1:2:4 mix ratio. Rate analysis involves calculating the total cost of materials, labor, tools, and overheads required to complete a unit quantity of work. For cement concrete in 1:2:4 mix, 1 part cement, 2 parts sand, 4 parts coarse aggregate, the analysis is typically done per cubic meter, m superscript 3. Step-by-step rate analysis, for 1 cubic meter of concrete. 1 material requirement for 1 cubic meter, dry volume equals 1.54 cubic meters. Dry volume includes voids and wastage. Mix ratio equals 1, 2, for rightward arrow total equals 7 parts. Cement equals 1/7 times 1.54 equals 0.22 m superscript 3. 1 cubic meter of cement equals 28.8 bags. So, 0.22 times 28.8 equals 6.34 bags, 6.5 bags. Sand equals 2/7 times 1.54 equals 0.44 m superscript 3. Coarse aggregate equals 4/7 times 1.54 equals 0.88 m superscript 3. 2 Material cost, example rates. Rates vary regionally, these are assumed for illustration. Cement, 6.5 bags at Indian rupee 730/bag, equals 4,745 Indian rupees. Sand, 0.44 cubic meters at 1,200 Indian rupees per cubic meter, equals 528 Indian rupees. Aggregate, 0.88 cubic meters at 1,600 Indian rupees per cubic meter, equals 1,408 Indian rupees. Right arrow total material cost equals 4,745 Indian rupees plus 528 Indian rupees plus 1,408 Indian rupees equals 6,681 Indian rupees. 3. Labor cost. Masons, laborers, helpers, 1,800 Indian rupees per m superscript 3, approximate. 4. Tools and plants, TNP. Cost for mixing, laying, compaction tools equals 200 Indian rupees per m superscript 3. 5. Water charges. Approximate 50 Indian rupees per m superscript 3. 6. Miscellaneous and sundries. Wastage, supervision, etc. equals 100 Indian rupees per m superscript 3. 7. Contractor's profit, 10 to 15%. Let's assume 10% of above total, before profit. Subtotal equals 6,681 Indian rupees, material, plus 1,800 Indian rupees, labor, plus 200 Indian rupees plus 50 Indian rupees plus 100 Indian rupees equals 8,831 Indian rupees. Profit equals 10% of 8,831 Indian rupees equals 883.1 Indian rupees. Total rate per m superscript 3 of 1:2:4 cement concrete equals 8,831 Indian rupees plus 883.1 Indian rupees 9,714 Indian rupees. White heavy check mark summary, per m superscript 3 of 1:2:4 concrete. Item. Quantity. Rate. Amount, Indian rupee. Cement. 6.5 bags. Indian rupee 730/bag. Indian rupee 4745. Sand. 0.44 m superscript 3. Indian rupee 1200/m superscript 3. Indian rupee 528. Coarse aggregate. 0.88 m superscript 3. Indian rupee 1600/m superscript 3. Indian rupee 1408. Labor. Indian rupee 1800. Tools and plants. Indian rupee 200. Water charges. Indian rupee 50. Sundries and overheads. Indian rupee 100. Contractor's profit. Indian rupee 883.1. Total. Indian rupee 9714. 13. Quetzales, what is the purpose of bid security? In which conditions it is forfeited and returned back to the respective bidder? Answer, purpose of bid security. Bid security, also called earnest money deposit, EMD, is a financial guarantee submitted by bidders along with their bids in a tendering process. Its main purposes are to ensure sincerity of the bidder in participating, to discourage frivolous or non-serious bids, to protect the interests of the client/owner in case the selected bidder fails to honor the bid. Conditions for forfeiture of bid security. Bid security is forfeited, not returned, when the bidder withdraws the bid after submission and before the bid validity period ends, fails to sign the contract agreement after being awarded the work, fails to furnish the required performance security or other required documents in time, provides false information or engages in fraudulent practices during bidding. Conditions for return of bid security. Bid security is returned to the bidder when bid is rejected during evaluation, bidder is not selected as the successful bidder, after award to someone else, successful bidder signs the agreement and furnishes performance security as required. 14. Quetzales, explain in brief about the maintenance of airport runway. Answer: the maintenance of an airport runway is crucial to ensure safety, functionality, and efficiency of aircraft operations. It involves routine inspections, repairs, and preventive measures to keep the runway in optimal condition. Types of runway maintenance. Routine maintenance. Regular cleaning, rubber removal, and minor crack sealing. Checking for foreign object debris, FOD, and removing it promptly. Inspection of runway lights and markings. Preventive maintenance. Applying seal coats, overlaying surfaces before deterioration occurs. Joint sealing and drainage maintenance to prevent water damage. Corrective maintenance. Repairs after identifying potholes, cracks, surface depressions, or structural damage. Reconstruction of damaged runway sections if needed. Emergency maintenance. Rapid repairs after accidents, natural disasters, or unexpected damage. Key activities in runway maintenance. Pavement inspection using visual checks and instruments, example skid resistance tests. Crack sealing and pothole patching. Rubber deposit removal, from aircraft landings. Drainage system cleaning to avoid water logging. Repainting runway markings for visibility. Lighting system maintenance, runway edge lights, threshold lights, etc. FOD checks before and after each day's operations. Importance. Ensures aircraft safety during takeoff and landing. Prevents runway closures and operational delays. Prolongs the service life of the runway. Complies with aviation authority standards, example ICAO, FAA. 15 Quetzales, what is the water-cement ratio and its effect in strength of concrete? Also explain briefly the factors affecting strength of concrete. Answer: water-cement ratio, W/C ratio. The water-cement ratio is the ratio of the weight of water to the weight of cement used in a concrete mix. Water-cement ratio equals weight of water/weight of cement. Effect of W/C ratio on strength of concrete. Lower W/C ratio, example 0.4 to 0.5. Higher strength. Less porosity. Better durability. Higher W/C ratio, example greater than 0.6. Lower strength. Increased porosity. Higher risk of shrinkage and cracking. Small orange diamond key rule: as the water-cement ratio increases, the strength of concrete decreases. Factors affecting strength of concrete. Water-cement ratio. Most critical factor influencing strength. Curing conditions. Proper curing ensures complete hydration and improves strength. Quality of cement. Type, grade, and freshness of cement affect strength. Quality and grading of aggregates. Well-graded, clean, and hard aggregates contribute to higher strength. Mixing time and method. Uniform and thorough mixing ensures proper bonding. Compaction. Proper compaction removes air voids, increasing strength. Age of concrete. Strength increases with time, notably up to 28 days. Temperature and weather. Extreme temperatures can affect hydration and setting. Admixtures. Use of plasticizers, retarders, etc., can alter strength behavior. 16 Quetzales, define the terms duty, delta, and base period that used in crop water requirements. Derive the relation between duty and delta. Answer: definitions of irrigation terms. Duty, D. It is the area of land, in hectares, that can be irrigated with 1 cubic meter per second, (cubic), of water flowing continuously during the base period. Unit, hectares/cubic. Delta, delta. It is the total depth of water, in cm, required by a crop during its entire base period. Unit, cm. Base period, b. It is the total time period, in days, between the first watering and the last watering of a crop, i.e., the crop growing period. Unit, days. Relation between duty and delta. Derivation. D equals duty in hectares / cubic. Equals total depth of water supplied in meters. B equals base period in days. If we take a field of area d hectares, water supplied to the field corresponding to the water depth meters will be equals x d hectares meters. Equals d times delta times 104 equals d times 104 cubic meters. 1. Again, for the same field of d hectares, 1 cubic of water is required to flow during the entire base period. Hence, water supplied to this field equals 1 times b times 24 times 60 times 60, m3 equals 1 times b times 24 times 60 times 60, m3. 2. Equating equations 1 and 2, we get d times delta times 104 equals b times 24 times 60 times 60 d times 104 equals b times 24 times 60 times 60. Delta equals b times 24 times 60 times 60, slash, d times 104, equals 8.64 b/d meters. For watching.